We use the new operator in C++ the same way that we use new in Java, that is to allocate memory for some object or array or anything actually, and we allocate this memory from the heap. So since pointers can refer to variables, we really don't need to have an identifier for some of these objects. We can dynamically allocate variables, and it's this operator new that creates these dynamic variables, and we don't need identifiers to refer to them. All we need is just a pointer. So that is, we can say something like this. We don't have to have assuming that p1 is, for example, a pointer, we can say p1 is equal to new int. That is, there is no variable for this new int. We will have a pointer referring to it, but there is no variable like we had before when we used the address of operator. Okay, so that said, this single statement causes a lot of problems for me, because I think a lot of students see this and think they have to use it, and you don't. This particular statement is completely useless. There is just no need to ever do anything like this. Okay, so if you find yourself writing a statement like this, you must think that something is wrong, because there's never going to be any need to use this. This is just an illustration, and what it really does is actually create an array of size 1. That's essentially what it does. And we never have to create an array of size 1. Okay, so almost always you'll need more than one element in an array. So this statement, once again, is completely useless. This is just an illustration that the book uses, and unfortunately every year students think that they have to use this, and there's really no reason. Let's take a look at how you would actually set up arrays. So that is using dynamic memory allocations. We'll take a look at how to access arrays, how to set up arrays and use arrays that are allocated on the stack first. That's how we've been using arrays and objects. And then we'll start switching to using the new keyword or the new operator. Okay, so here is a simple example. So I set up a variable and set it equal to 10, and then I allocate memory on the stack for it. So this is the regular kinds of arrays we've been setting up, not available in Java, since in Java you have to allocate memory on the heap. So this is the old style C or C++ style arrays that you cannot do in Java. You can set the individual members equal to values. You can assign values to individual members, a sub 0, a sub 1, so on. You can write a loop, for example, to assign values to all the locations, and you can index back and forth. I'm hoping this part should make sense. And this is all, starting from here, this is all would be legal in Java too. You can send an array as a parameter or argument, an argument to a function that takes an array as a parameter. In this case, I happen to call them both A, but you don't have to. And you can remember that in C++, you need to know the size when you call a function. That's because the array doesn't have a length data member. So you would use this size variable or parameter, in a loop like this. You would say for int I equals 0, I less than, in this case, size minus 1, I plus plus, and do some kind of processing with that array. Okay, so all of this will compile. I'm just going to check it out. I think I already compiled and ran it. Compiles, and it runs. Okay, so you can, if you want, you can pause the video and try this example out. It's just a simple main function, assigns values to this 10 location array, calls a function, and then prints out all of the values, and here they are. Okay, so now how would this change if you use dynamic memory allocation? Well, first let's talk about where this memory is allocated. This memory is allocated in the stack frame for main. Remember that whenever you call a function, you get a completely new stack frame. So when you call process, you no longer have direct access to this old A array. What you have is a pointer. So it turns out this is just a pointer. And this is passed into the stack. And in the stack you have access to this pointer. And so you can use this array as if you were, well, alright, so you can use this array in here, and you have a brand new stack activation frame in which you have a brand new int I and so on. And size is also passed into that stack frame. When you exit, that memory is gone. And so same thing happens here. When you exit this function, this array A, which is on the stack, the memory for that is removed because the stack activation frame for main is gone. Sometimes you might want to make an array or an object stick around for longer than you are in, let's say, a function. So I'm not going to do that here, but I'll show you how to do that if you want to have an array stick around. For example, you could set up an array inside this, allocate it on the heap, and then exit and have that array still stick around. Okay, so in this particular case we were using this array A passed in from the calling function main, but you could also, for example, set up an array in here and have it be around even after this function exits. And that's the reason why we want to use dynamic memory in the first place. We want to have objects that will stick around beyond the lifetime of a single function. Okay, how do we do that? How do we set up how do we use memory from the heap? This is what you do. First of all, you say that A is a pointer. And then you say equals new int. So apart from this star, this is sort of what you would expect to see in Java. So in Java you would see something like this, but doesn't work in C++. So if you had something like this would work in Java. Unfortunately not in C++. It would be nice. In C++, the difference is you would have to use something like this. Okay, save it, compile it, and run it, and everything works just as before. Now here's the thing. In this case, I don't have to worry about things like taking care of deallocating memory that I allocate. So once again, this is not the kind of situation where we would need dynamic memory allocation. In this particular example, we don't actually need dynamic memory allocation. This is just an example showing you how to do it. Let's just assume that this is not a main function, but some other function that's called by main. In that case, what we would be doing is we would, let's say, let's just actually do that right now. Let's say we have a void compute. All right. And then what I will do is I will take all of this stuff out of main and put it in here. And then what I will do is I'll just call compute from main. So you guys know that we could just as well have done everything in main, but I'm just trying to show you the kind of situations where you would need to do something like this. So now, ordinarily, when you call compute from main, variables like n and actually a2, this variable is only going to be around from this point, from the point at which they're declared, to the end of the function. After the end of the function, the variable a is gone, but this memory that's allocated by this new is going to still be around. Okay, it's actually going to stick around, so you could call compute a couple of times. And each time, what you will end up doing is you will end up allocating memory. All right, and that's going to stick around even after compute is done. If we had used the stack, that would not be happening. If we had used the stack like we had before, that is, if we have this situation, now every time you start up this compute, you allocate a new chunk of memory on the stack. You do a bunch of processing. As soon as you exit, this complete array is gone. Okay. So if I compile this and run this, this will work. And we call it twice. We actually have two completely different arrays that are going to be allocated on the stack and released from use. However, if you use dynamic memory allocation, we can do something like this. New int n, and if you want, you could return this. Print it out and return a. That's perfectly legal. That's actually that's one of the reasons why we use dynamic memory allocation. And what we could do is we could do the printing in the main function. I'm not going to do it right now because we need other things to be set up. Okay, so here's the thing. If you're not going to return it, so you could actually return an array that you allocate inside a function and have it be used in the calling function. So we could take the return value and use it. Okay, so that's why we would want to use dynamic memory allocation. So now that you know that, let me show you one other thing where okay, so so let's take a quick look at this. So we call compute twice. Each time you're going to allocate a complete new array. If we don't deallocate that memory and we call compute, let's say 100 million times, you're going to continue allocating memory that's sort of set aside for us but never used. Okay, so let me go back to making this a void function because I'm not going to use the return value right now. You can use the return value, but excuse me, I'm not going to use the return value. Alright, so now let's assume that the compute is called 100 million times. Each time you allocate an array of 10 ints, that's 40 bytes, that's 40 times 100 million, which would be about 4 megabytes. 4 gigabytes. So that will use up the entire memory of the system if you have a 32-bit system. And so that's not good. So what you want to do is every time you see a new, if you're done using it, what you want to do is delete. And now, every time you allocate memory, you do something with that memory, you do some processing, print something out, and then when you're done using that memory, you delete that memory, and that memory is deallocated. So this is the allocation point from the heap. And typically what you want to do is anywhere you see a memory allocation step from the heap that is using new, you want to see a memory deallocation so that your program doesn't run out of memory. And now you could call this compute function 500 million, billion times, and you will never run out of memory because every time you allocate memory, you deallocate it and you're safe. So this is the kind of thing you want to be able to do with dynamic memory allocation. You can allocate memory and have it be around well past your function execution, but at the same time you also want to make sure that eventually that memory is deallocated so that your program doesn't run out of memory.